Thank you. I can only give as an excuse that Bose-Einstein condensate can also be trapped because, of course, gravity does not distinguish between different masses. And just to start on a light note, let me show the following prologue, which says what the principal investigator would like to be trapped. If these are elementary particles, then gravity is much too weak as compared to other forces at those scales. If they are massive bodies, exemplum stars or compact objects, then there are no physically motivated, sufficiently strong gravitational waves to achieve this. This may sound as a joke, but for me it was a very painful joke, because I applied for a grant some time ago, and the grant was rejected on the grounds that an expert expressed his negative opinion. Can you imagine there is a body of people, a panel, as in many countries they do it that way. This body finds an expert in this field, and the expert apparently did not know what Galileo proved, because what Galileo proved was that the action of gravity does not depend on the mass. And moreover, if one thinks for a while, if gravity is too weak to hold small particles like elementary particles and atoms, how can we breathe on Earth? What is the force that is holding air close to the surface of the Earth if it is not gravity? So for young people, this is a lesson that physics is just one field, and one should not concentrate on something specific, because one should always have a view of the whole. So with this in mind, now we go further. What are these two pictures showing? They are showing a great similarity between the action of the electromagnetic field and gravitation. I plotted these two curves. They show how a charged particle, in this case, here, somehow I cannot engage the laser pointer, but that's no problem. Here, this shows similar situations. Marzena will help me, I'm sure. Which button I press? This, I pressed this one. Maybe my finger is too... Yes, there is this. Yes. These two trajectories are projections on the plane showing how a particle moves in a field that has angular momentum. Now, electromagnetic waves have angular momentum, and we heard some about this quality of electromagnetic waves, but gravitational waves also have angular momentum. And this similarity shows that the mechanism is very similar. This is the trajectory in 3 dimensions. What I shown before was the projection on the plane. Now we see these trajectories in electromagnetism and in gravitation, shown in 3D. So, where does angular momentum of gravitational wave come from? This is the formula for the angular momentum, which can be calculated by high school pupils, because it only requires the knowledge of the action of gravity and centrifugal force. If there are two bodies that are revolving around each other, they have angular momentum, obviously. And the amount of angular momentum depends, of course, on the gravitational constant. It depends on the mass, and it depends on the radius of this body from the center of the rotation. Now it is nice to express this in terms of the Schwarzschild radius. Here is Rs. What is Rs? Is the Schwarzschild radius. It is the radius connected with gravity, which characterizes the size of a black hole. And here is a numerical example. If there are two black holes, and these are the black holes that were seen in experiments where they detected gravitational waves, they have about 30 solar masses, and they are spiraling at various distances in the process of shrinking. At some point, they will be at the distance of 10 Schwarzschild radii, and they have angular momentum. To compare this angular momentum with something we know, it is 100,000 times the angular momentum on of the Earth on the solar orbit. The Earth going around has angular momentum. It also produces gravitational waves, but of course they are negligible. So the angular momentum of two black holes is quite large. Now, why I show this formula? Because notice the dependence on the radius. When the radius shrinks, angular momentum becomes smaller and smaller. So what happens to this angular momentum? Angular momentum is emitted by the system because of the conservation of angular momentum. If the mechanical angular momentum goes to zero, this is found in the gravitational wave, which carries the missing angular momentum. So this is an even more important quantity. It is the luminosity, angular momentum luminosity. What is luminosity? For normal optical signals we know, but this is just the amount of angular momentum that is emitted per unit of time per second. And this formula now is not trivial. It requires the knowledge of the whole mechanism, how black holes rotating radiate. But at the end, people who have done this calculation some years ago discovered that the formula is fairly involved. The first part here is fairly complicated. If you express this in natural units, and the natural units involve the Schwarzschild radius, the formula becomes extremely simple. You may wonder whether dimensions are okay, because on the right-hand side we have mc squared. Mc squared is the energy, whereas angular momentum does not go immediately with energy. However, angular momentum has the same dimension as the Planck constant. And the Planck constant, as far as dimensions go, can be expressed as the unit of time times the unit of energy. Therefore, if you divide by time, the rest is the energy. And now we have again a numerical example. Two black holes, the same as before. They are spiraling at a distance of 10 Schwarzschild radii, emit per second 6 million times the angular momentum of the Earth. So one now can see that there is a lot of angular momentum in gravitational waves. It is not easy to detect this, because to detect angular momentum, we must have a large area of observation, whereas the area that is really applicable in this case is minimal, because it's a very small apparatus on the cosmic scale that would not show the angular momentum. So let's go further, and what do we have here? Well, there are famous Bessel beams in optics, which are the working horse for opticians, because they use Bessel waves to describe the electromagnetic waves that carry angular momentum. These waves can be derived, and this is something that it's worth remembering. If you just take the Bessel function of the transverse momentum times the distance from the center, and there is this phase factor, then this generating function can be used to produce the full solution of Maxwell equations. This is something what I like very much because it simplifies the solution of Maxwell equation greatly. You don't have to go and solve it in the three-dimensional form. You can use the scalar solution of the wave equation, and then by differentiating you get electric and magnetic field or whatever. Here are the quantum numbers that characterize this wave. There is helicity, which is the sign here, energy, because Bessel functions are monochromatic, and that is why they are not really perfect, because there are no truly monochromatic waves, but when you are close to the center of the beam, that is a fairly good representation. Now Hm is the z component of the total angular momentum carried by this wave. In quantum mechanical language, the electromagnetic wave here is an eigenstate of the z component of angular momentum. And of course, it is also an eigenstate of the z component of momentum. So it's a very simple wave, especially when you use the quantum numbers of the photon that makes such a wave to characterize this wave. Now, this shows a basic character of a wave that carries angular momentum. The wave surface has this spiral character. Now, when we want to use this for gravitational waves, it's amazing that the same generating function, this one, can be used to generate gravitational wave which has angular momentum. All one has to do is to differentiate 4 times instead of 2 times, and you get the gravitational waves that carries angular momentum. So now we use the basic equation of motion of particles in the gravitational field, and obviously at the beginning we have 2 coefficients. One is the inertial mass here, and the second is the gravitational mass, and Galileo and then Einstein recognized the importance of this equality because these masses are equal, and therefore mass disappears from the equation of motion. And this is why this expert that wrote this opinion about I grant proposal missed the most important part. In gravity, mass does not matter. All bodies move the same way regardless of their mass. So here we have this equation, and what I want to do with this equation, apply this equation for a gravitational wave that carries angular momentum to see what happens. So this equation, of course, determines the geodesic curve, and the geodesic curve here can be found in the following way. First, I notice that those who do numerical gravity, and there are large groups who are now involved in such projects, argue that m equals 2, angular momentum equals 2, is the main component of this radiation which is dominating the rest. Why 2? One can understand that. This is connected with the helicity of the gravitational wave. Electromagnetic waves have helicity 1. Therefore, for electromagnetism, m equals 1 is most important. For gravitational waves, m equals 2 is most important. Now, because Bessel beams as you have seen from this formula, have the cylindrical symmetry, there is one distinguished trajectory which is obvious, and that is the motion along the center of the beam. Because the Bessel function vanishes there, so there is no action of the gravitational field which can be seen mathematically when one finds what is the Christoffel symbol in this case, and the Christoffel symbol in this case vanishes. Therefore, we have a uniform motion here along the center of the beam. And why this observation is important? Because in general relativity, which is invariant under all possible transformations of the coordinate system, the formula for the trajectory is very often meaningless, because you can change the coordinate system and you get a different formula. However, in this case, it's a geodesic motion along a distinguished line, and therefore we can use this as a starting point. And what I use then is what is called geodesic deviation, because the important question is now the following. We have this geodesic trajectory. The question is, if we depart slightly from this geodesic trajectory, will this trajectory still be trapped? Will it still be close to the center of the beam? Because that would prove that if something is near the center, it will stay close to the center. So this is an equation which is derived in the following way. Namely, we consider two trajectories, and the picture on the next transparency shows. We have one which is reference trajectory, and we study small variations of this reference trajectory, and this is how this equation is obtained. All higher order corrections were neglected. Only the linear part in the difference between these two trajectories. And one gains a lot, because as you see in this equation now, we do not have metric, we do not have Christoffel symbols, we only have the geometric characterization of the gravitational field, namely the curvature tensor, the Riemann tensor. Okay, my chairman says I have 5 minutes more, and I'm sure I can show. One then calculates this Riemann tensor for the gravitational Bessel beam, and it's a mess. However, there are two simplifications. First, we know that m equals 2 is dominant, and the second, we are staying close to the center of the beam. And therefore, things which look very complicated, I didn't write all the components. As you know, Riemann tensor has many more components that's shown here. Each component is a combination of various Bessel functions. However, if one uses this assumption that m is equal to 2 and we are staying close, we get equations that could be given to a student of mechanics to be solved. The only slight complication is that the right-hand side depends not only on the coordinates, but also has functions of omega t, which means that we have the situation which should be treated by transformation to a system in which the time dependence is eliminated. And this system is just the system that is rotating around the center of the beam with the angular velocity omega divided by 2. And when one does this transformation, one obtains very nice equations, and they do have here what I marked in red, the terms which are associated with the Coriolis force. And in this way, my talk is connected with other talks. For example, Wolfgang Ketterle mentioned at the beginning of his lecture that there is a Powell trap, and Powell trap is again, using the same mechanism, the Coriolis force, to stabilize the motion. It is not quite the same as the Paul trap, because the term which does not contain the derivatives with respect to time, in both equations have the same sign. It is a repulsion. So one would think at first that this orbit cannot be stable. However, it is, because one can calculate the frequencies here, and the frequencies are positive. Therefore, the motion is stable. So here is the motion. I go back to the inertial frame, and I transform the solution of these simple equations. As you see, there is no higher mathematics here, just ordinary differential equations. And this is the trajectory in the xy plane, which I have shown before. It is obtained by integrating these simple equations. So the conclusion is that gravitational waves may carry with them all kinds of cosmic debris. There is this gravitational wave which emerges from the binary system, and when it encounters something on its way to us from these two black holes, it may trap the particles which it finds on its way to us. And the trapping of these bodies is due to the Coriolis force. Thank you.